Welcome to Lab to Lecture. This is the revision playlist for Cambridge IGCSE Chemistry. Today, we are breaking down Topic 2, Atoms, Elements and Compounds in a few minutes. Quick, clear and to the point. Let's dive in. An element is a substance that cannot be broken down into simpler substances. An element is represented by a chemical symbol, and a chemical symbol can be one letter or two letters. If the symbol contains two letters, the first is always in uppercase and the second is always in lowercase. Each element contains only one type of atoms. And elements can exist as atoms or molecules. When the element exists as atoms, it's said to be a monatomic element like noble gases. All of them are found in nature as separate atoms. Other elements exist in nature as molecules, and a molecule is a group of two or more atoms that are chemically combined. Elements could be diatomic, and all elements that are diatomic are collected in one word, Hunkel-Breff: hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, and fluorine. Those are all the elements that exist in nature as diatomics. Ozone exists in nature as 3 atoms of oxygen together in one unit, phosphorus 4 atoms in one unit, and sulfur 8 atoms in one unit. A compound is a substance containing 2 or more elements that are chemically combined in fixed proportion. A compound can be represented by a chemical formula. The chemical formula tells you about the types and proportion or ratio of different atoms in that compound. As an example, water, H2O, we have hydrogen and oxygen, and the proportion or ratio between them, 2 atoms of hydrogen per 1 atom of oxygen in one unit. Now let's compare between elements and compounds to summarize everything. Carbon and oxygen. Carbon exists as a monatomic element and oxygen is a diatomic element. An example of a compound, carbon dioxide, CO2, it has carbon and oxygen together chemically combined, and the ratio between them is 1 carbon atom to 2 oxygen atoms in one unit. Remember, the element has only one type of atom, while a compound contains 2 or more types of atoms. Any element cannot be broken down into simpler substances. A compound, on the other hand, can be broken down into elements or simpler compounds by thermal decomposition or electrolysis. A mixture is made up of 2 or more substances that are not chemically combined in any ratio. So simply, when you mix different substances physically, then you can make a mixture. Mixtures can be made up of elements and or compounds. So you can have a mixture of 2 elements, 2 compounds, or 1 element and 1 compound. Examples: brass, which is a mixture of copper and zinc. Stainless steel, which is a mixture of iron with other elements such as chromium, nickel, and carbon. Now let's summarize everything between mixtures and compounds in that table. An example of a mixture: when you mix sulfur element and iron elements, you have a mixture of 2 elements. An example of a compound: when you heat them together and you form iron 2 sulfide. So now iron and sulfur, they are chemically combined together to give you iron sulfide. Now regarding the separation of a mixture, you can separate the mixture using physical processes like in that example you may use magnetic separation, and in other examples you may use filtration or distillation, and those are said to be physical processes. To separate a compound, on the other hand, you need to use chemical processes as thermal decomposition or electrolysis. The properties of the mixture are the same as those of its components, while properties of compounds are different than those of its constituent elements. As you may see here, iron 2 sulfide is black powder, but the constituent elements, sulfur and iron, they have different colors. When we form mixtures, we can use any proportion, but in compounds, we have to stick to fixed proportion between elements. Any atom has two main regions, nucleus in the center, and outside nucleus we have electrons. So we have three subatomic particles. We have electron, neutron, and proton. The relative mass of an electron is 1 over 1840. For a neutron it's 1, for a proton is 1. The relative charge of an electron is -1, a neutron is neutral, it's 0, and a proton is +1. Proton number, sometimes we call it atomic number, is defined as the number of protons in the nucleus of an atom. Mass number, or nucleon number, is defined as the total number of protons and neutrons in the nucleus of an atom. Now we're going to discuss how electrons are arranged in an atom in what's known as electronic configuration of elements or ions. In the syllabus, you'll be asked for elements with a proton number from 1 until 20. The first shell of any atom takes a maximum of 2 electrons, but the second shell can take a maximum of up to 8 electrons, and the third shell takes up to 8 electrons. And the last element that you are asked to make its electronic configuration is calcium. In a periodic table, we have vertical columns, which are known as groups, and we have horizontal rows, which are known as periods. The last group of the periodic table is known as group 8 noble gases, and they have full outer shell electrons. And they have full outer electron shell. The group number in the periodic table tells you about the number of outer shell electrons, but the period number tells you how many occupied electron shells we have. Let's take magnesium as an example. It's found in group 2, that's why it has 2 outer electrons. And it's found in period 3, that's why it has 3 shells around the nucleus. Isotopes are defined as different atoms of the same element that have the same number of protons but different number of neutrons. As an example, chlorine, it has 2 isotopes, chlorine 35 and chlorine 37. So both of the isotopes have the same number of protons, 17 protons, but chlorine 35 has 18 neutrons, chlorine 37 has 20 neutrons. To represent an element, we use a symbol of that element, and to the lower side left of it, we put the atomic number, and upper left of it, we put the mass number. As an example, carbon can be written as C612, 6 atomic number and 12 mass number. However, in the periodic table, you may find carbon written this way, C, and then 12 down and 6 up. That's the version that you're going to get in the exam. Mass number down and atomic number up. Isotopes of the same element should have the same chemical properties. And the reason behind that, because they have the same number of electrons, and electrons are responsible for the chemical properties. So they have the same electronic configuration and the same chemical properties. If you are asked to calculate the relative atomic mass of an element, all what you need, the relative masses and abundances. Chlorine exists in nature in 2 isotopes, chlorine 35 with a relative abundance of 75% and chlorine 37 with a relative abundance of 25%. So all what you need to do is take the mass, multiply by the percentage. 75 will be 75 over 100, and 37 is the mass of the second isotope. It's found in nature as 25%, it means 25 over 100, and add them together, then you're going to get 35.5. That is the mass that we write in the periodic table. So in the periodic table, we never write one of the 2 isotopes, we just write like the average between them. Ions are atoms that have lost or gained electrons. To form positive ions or cations, atoms have to lose electrons. And the reason behind that, they need to reach the stable electronic configuration of the noble gas. So that's why they are tending to lose or gain electrons. In case of metals, they lose electrons, they form positive ions or cations. As an example, sodium, it has one outer electron, but non-metals, on the other hand, they tend to form negative ions or anions because they gain electrons. And once again, they need to achieve this stable electronic configuration of a noble gas. So here we have the electronic configuration of chlorine, and it gains one electron from somewhere outside the chlorine, and then it turns into an ion, a negative ion or anion. We call it chloride ion. Any ion has to be included between square brackets, and then we put the charge to the upper right corner of it. An ionic bond is defined as a strong electrostatic attraction between oppositely charged ions. In the exam, you'll be asked to draw a dot and cross diagram, and we use dots to represent the electrons from one atom and crosses to represent electrons from another atom. Scientifically, all electrons are the same, but we're using dots and crosses to show that electrons come from different atoms. Sometimes we simplify the diagram by drawing only the outer shell electrons. Here we have an example between group 1, sodium, metal, and group 7, chlorine, non-metal. Sodium loses its outer electron to chlorine, and as a result, sodium cation will be formed and chloride anion will be formed in a compound known as sodium chloride. A second example, lithium fluoride between lithium positive ion and fluoride negative ion. As you may notice here, the lithium has lost its outer electron to the fluorine atom to form a fluoride ion and lithium cation. A third example, potassium chloride. Potassium has one positive charge and chloride has a one negative charge. Ionic compounds exist in giant lattice structure, and that's simply an ionic compound in a regular arrangement of alternating positive and negative ions. As an example, sodium chloride. Here, as you may see here, X can represent the positive ion and the Y can represent the negative ion. So you have alternating positive and negative in the 3 dimensions, and they are found in a giant structure. It means you have plenty of them. You have millions of them in just a small sample. The physical properties of ionic compounds are having high melting and boiling points, and that happens due to having strong electrostatic forces between ions in the crystal lattice, so we need a lot of energy to separate them. A second property, having good electrical conductivity when they are aqueous or molten, but poor electrical conductivity when they are solid. Let me tell you that for a substance to conduct electricity, it should have charge carriers, and charge carriers are whether free electrons or free ions. Free, I mean they can move. In case of an ionic compound, since ions are locked in place, they can't move in the solid state. That's why they have poor electrical conductivity, because ions are not free to move in the solid form. But when you dissolve a piece of salt, let's say, in water to make aqueous solution, then ions are free to move. The same applies here if you have a molten sample. Ions are free to move in the molten or liquid state of an ionic compound. A covalent bond is formed when a pair of electrons is shared between 2 atoms, leading to a noble gas electronic configurations. Here we have the examples in the syllabus. The first one is the molecule of hydrogen. So 2 hydrogen atoms, each of them has a single outer electron. They are going to share their electrons and they form hydrogen molecule. And each atom of them would have the electronic configuration of the noble gas helium. When 2 chlorine atoms form a covalent bond, 2 electrons are going to be shared between the 2 atoms to form chlorine molecule. Hydrogen chloride molecule is formed between 1 atom of hydrogen and 1 atom of chlorine, and you have 2 shared electrons in between. In a methane molecule, you have a central carbon atom and 4 hydrogen atoms. each hydrogen atom is going to share its outer electron with one of the electrons of the carbon. In ammonia molecule, we have a nitrogen central atom and 3 hydrogen atoms. And as you may notice here, 2 electrons of nitrogen are not shared with hydrogens. You have to practice drawing those dots and crosses diagrams. In water molecule, oxygen in the center and 2 hydrogens bonded to it, and we have 4 electrons that are not included in the bonding. An oxygen molecule is formed when an oxygen atom shares 2 of its electrons with another oxygen atom. In nitrogen molecule, 3 electrons are going to be used in bonding from each atom, and we have 2 electrons that are not used in bonding for each nitrogen atom. That's a bit challenging. Methanol, when we have carbon that's bonded to 3 hydrogen atoms, and bonded to carbon we have 1 oxygen, and bonded to oxygen we have a hydrogen, so that's methanol, CH3OH. As you may notice here, the bonding is single bonds between carbon and the 3 hydrogens, and single bond between carbon and oxygen, and single bond between oxygen and the hydrogen. And also notice here that the oxygen has 4 electrons that are not included in bonding. The key principle here, if you count the electrons for each atom, you're going to find that each atom has a stable noble gas electronic configuration. Covalent bonding is formed between 2 nonmetals. Let's say we have a sample of hydrogen gas. And as you may remember, hydrogen exists in nature as diatomic molecules. So you may have a diatomic molecule of hydrogen and another neighboring diatomic molecule, and so on. Now, each of these molecules is known to be a simple molecule, and each of these molecules are connected to the neighboring molecule through what's known as intermolecular forces. Now, these intermolecular forces are weak forces of attraction. They are not as strong as the bonding in between the 2 atoms, which is the covalent bonding, the strong covalent bonding. So here we have weak intermolecular forces, while in between we have strong covalent bonding. So we say that simple molecular compounds have low melting points and boiling points. And once again, the reason, because of having weak intermolecular forces between molecules, while we have strong covalent bonds within each molecule. So to split those molecules from one another, you just need a little energy, and we don't require a lot of energy to break the intermolecular forces between them. And that's why most of these simple molecular compounds, they are found in the gaseous form. But it's worth noting that the giant covalent substances, as we're going to discuss in a minute, have higher melting and boiling points because we have strong covalent bonds in the structure. The second property is having poor electrical conductivity because we don't have charge carriers. We don't have free electrons to move through the structure, and we don't have ions. If we have plenty of the nonmetal atoms bonded together, then we have what's known as giant covalent structure. We have 3 examples of giant covalent structure. First, let me start with the comparison between diamond, which is just carbon atoms bonded to each other in 3 dimensions. So we have a 3-dimensional structure. The other structure is graphite. Also is formed of carbon, but the structure here is different. In diamond, as you may notice, each carbon atom is bonded in 3 dimensions to neighboring carbon atoms, and the bonding is covalent bonds. That's why the diamond is extremely hard, and let's say that's the hardest natural material that we have on Earth. However, in graphite, as you may notice, carbon atoms are bonded to each other, but in the form of layers. So within each layer, the bonding is covalent. So here we have covalent bonding, but between one layer and a neighboring layer, the bonding, as you may notice here, is weak forces of attraction. It's intermolecular forces of attraction between the layers. So here in between, we have weak intermolecular forces. That's why the layers are able to slide over each other, And that's the reason why we call graphite to be soft. Soft because layers can slide over each other, and that's why also we can use it as a lubricant. So as you may notice here that each carbon atom is bonded to 4 other carbon atoms. So each carbon atom has used all of its outer electrons, and we don't have any free electrons to be delocalized or to move through the structure. That's why you expect diamond not to conduct electricity. However, here in graphite, each carbon atom is bonded to 3 neighboring carbon atoms, and each carbon atom has 1 free electron that has not been used in bonding. Now, these free electrons are able to move through the structure. That's why graphite conducts electricity, and this is a very, very important point. Graphite conducts electricity. Diamond does not conduct electricity. However, both of them, they have the same chemical composition, but they have different structures. Diamond can be used in cutting tools, as we said before, because it's the hardest natural material. Graphite can be used as a lubricant because it's soft and it has a slippery feel, and also graphite can be used as an electrode, as we're going to discover in electrolysis in topic 4, because it conducts electricity. Now, the third giant structure we have is SiO2, or silicon dioxide. It's very similar to diamond. As you may notice here, we have 3-dimensional structure. Atoms are bonded in the 3 dimensions. And that's why we have high melting and boiling point, because bonding here is covalent in all directions. And we don't have any free electrons to conduct electricity. That's why it doesn't conduct electricity. In metallic bonding, we have just metal atoms. And metallic bonding is defined as the electrostatic attraction between positive ions in the giant metallic structure and sea of delocalized electrons. This is a very, very important term. Sea of delocalized electrons, you're going to use it a lot. In the exam, you need to make larger spheres and in between smaller spheres, or you may use the symbol E negative, and you have to label the larger spheres as positive metal ions and the smaller spheres, or E minus, as delocalized or mobile or free electrons. Metals are good conductors of electricity, and the reason, because of having free electrons or free delocalized electrons that can move through the structure. Metals are malleable and ductile, and malleability is defined as the ability of being hammered or bent without being broken. Ductility is the ability to be pulled out into thin wires. When force is applied to a metal, layers can slide over each other without disrupting the metallic bonding, because even if the spheres of the cations, if they slide over each other, you still have the sea of electrons in between, and the electrostatic attraction between them still exists. So the metallic bonding still exists, and the metallic bonding is not disrupted. Finally, metals have high melting and boiling point, and once again, because of the strong attractions between positive metal ions and the mobile or delocalized sea of electrons. So as you may notice, in all of the properties of metals, we boil it down to the delocalized sea of electrons. I hope that helps. See you next time.